Thank you very much. And we will start with the presentation of Enzo Tagliazucchi. He will be presenting us really important work on how can we predict brain age from multimodal imaging and how those brain age predictions are related to social determinants of health and diversity. So we're going to start with the pre-recorded talk of Enzo Tagliazucchi. Thank you.
Hello, everybody. My name is Enzo Tagliazucchi. I will present the talk Higher Interactions to Track Brain Aging using a deep learning approach. This presentation was originally scheduled to have Sebastián Moguiner as a speaker, and he could not come to OHBM. And then I couldn't come, sorry, my apologies. So I will nevertheless present the talk instead of him. And it's important to tell you that this work was mainly done by Sebastián, with supervision of Agustín Ibáñez at the Latin American Brain Health Institute in Chile. So if you want to take a look at the paper, it's published in Nature Medicine last year, and the first author is Sebastián. So the key questions we will be addressing in this talk have to do with brain aging and how to use in vivo neuroimaging data to estimate the biological age of the brain. Not only that, but we will also ask questions concerning how neurodegenerative diseases, mainly Alzheimer's disease and frontotemporal dementia, affect the biological brain age as estimated using multimodal models based on fMRI and EEG data. And then we will ask several questions concerning the effect of contextual or environmental factors on brain aging. For example, disparities, socioeconomic disparities, but also factors related to education, factors related to air pollution, and so on. And after we ask these questions concerning the factors that affect brain aging and get some answers, we will focus on how these different contextual factors that affect brain aging depend on different countries or different regions of the world. For example, Latin American countries, which are known to have higher levels of disparity and have a more challenging socioeconomical profile compared to high-income countries that are not located in Latin America. And we will, throughout all these questions, we will focus on whether these different factors or different contexts or regions affect brain aging in healthy individuals as well as patients. So how can we estimate the biological age of the brain using neuroimaging data? Well, this is a well-established procedure. Essentially, what you have to do is you have to obtain brain data, for example, structural imaging data or functional imaging data. This can be done using MRI, but also fMRI or even EEG, as we will use in this presentation. And then using a large database, you can construct a normative model that is a model trained on a population of healthy individuals, where the objective is to predict their age, their chronological age, based on the neuroimaging data. So this can be used to train a model, a machine learning model, for example, using cross-validation to estimate model parameters and also to assess the performance of the model. And after this model is trained and is estimated how well it does on the healthy population, it can be generalized to a different group of individuals, for example, patients, and then the prediction of the model can be understood as the biological age of the brain, so that it can be compared with the chronological age of each individual in the following way. So if we have the chronological age versus the predicted brain age using the model, and we have, in this example, 3 different individuals, what we can see is that one of the individuals has a lower biological age compared to what would be expected based on the chronological age, and we will say that the brain age gap, that is the difference between these two values, is negative in this case. And this participant is essentially younger in terms of his or her brain age compared to the chronological age. Then we have another example in which they are equal of both values. So we will say that this person doesn't have any brain age gap. And then we have the other situation in which this participant is showing accelerated brain aging because the brain age gap is positive. So this participant is older than what would be expected. So in this work, what we did is we obtained and assembled a large data set of individuals, both from Latin American and non-Latin American countries. For example, I'm showing here the distribution of the Latin American countries that contributed to this data set. So we have participants throughout several countries, and the large majority of these participants are healthy controls. But we also have patients with Alzheimer's disease, behavioral variant frontotemporal dementia, and mild cognitive impairment. So this database is essentially part of the Red Lab consortium, and we have a bit less than 3,000 participants from Latin American countries. And we also have, for a group of these participants, we have fMRI, and we also have a subgroup which also has EEG data, which we can use to estimate these multimodal brain aging models. Then we have the other part of the data, which is participants from non-Latin American countries. So these are countries located in Europe. These are countries that are also located in Asia, for example, Japan and China. And we also have participants from USA. Most of this data comes from the ADNI database, but we also have participants from the frontotemporal dementia neuroimaging consortium as part of LONI. And we also have a subgroup of these participants coming from the Red Lat dataset, especially those from the US. So we all have a similar comparable number of participants from non-Latin American countries. Also, we also have patients and controls. And then we have the following procedure to train and estimate the accuracy of these models to predict the brain age gap. So first, we do some standard pre-processing of the data. fMRI was pre-processed using fMRI prep and using standard procedures. This was parcellated using the AAL template, and so we end up with a set of 90 regions, each with containing the time series, the ball time series corresponding to each region. The EEG was processed also using similar standard procedures, which included bandpass filtering and also using independent component analysis to clean different sorts of artifacts. And then this was normalized using set scores, and it was transformed to the sources, so source localized using S-Loretta, also to the same set of regions, to the AL, to the 90 regions in the AL parcellation. And we also end up with 90 regions, 90 time series containing representing the EEG data source localized to each region in the AL template. So we have similar data. One is, of course, fMRI, and the other is source localized EEG for each participant. And to estimate the interactions, we use this high order interactions approach, which is basically a generalization of the Shannon entropy. So for each pair of regions, we consider the following. We consider first the time series of one region, then the other, and then we consider the time series of the rest of the regions, the remaining regions of the brain. So we essentially have three contributions, and then for each pair, we compute this with n equal 2. So we basically have the H is the Shannon entropy, the standard Shannon entropy of the field multivariate time series. And then we have each of the two regions that we're interested in here, subtracting the Shannon entropy of the rest of the brain and the other time series. And we have all the combinations here. So basically, this is what we do is we set n equal 3 here. And then we have, as I said, the two time series of regions of one of the regions, the other regions, and the rest of the brain. And we can compute then for each pair of regions, conditional to the rest of the brain, this high order interaction metric based on information theory. So we end up with connectivity matrices based on these information theory criteria. And then these connectivity matrices have a natural graph representation where we have nodes, and the connection between the nodes is this metric of mutual information we estimated before. Then we apply a data augmentation technique. Basically, the augmentation technique consists of getting matrices, connectivity matrices of participants which are in similar age groups, and then in creating another matrix, which is essentially an interpolation using a continuous parameter that is changing between 0 and 1. So we create new examples by interpolating the data we already have. And then this is the model is essentially a graph convolution model. So because there is somewhat arbitrary ordering of these rows and columns in this matrix, you cannot use a standard deep convolutional network with this as an input, because being close here in this space doesn't mean that these regions are actually close in the brain. So this is based on graph convolutional network, which takes the graphs as samples. So the similarity between the nodes is not in terms of Euclidean distance, but in terms of the strengths of the links that connect them. And then it does several convolution operations. In the case we have two graph convolutional layers to aggregate these nodes and links into reduced versions of the networks. And this is keeps iterating until we basically have a final layer where we get well, a single number, which is the prediction of the model, which can be understood in terms of the estimated age of the participant. So for the fMRI model, we have a good compared to what is the state-of-the-art prediction in terms of the R square and the F square metrics. This is trained and tested in the sample of non-Latin American countries. Using a bootstrapping procedure, essentially what is done is each node and link is removed several times from the network, then you estimate the accuracy of the model without that feature, and then depending on whether the model increase or decrease the performance, we have a metric of how important that node and link was for the prediction. So this is repeated several times using this bootstrapping method to estimate a metric of importance for each feature. So we have essentially nodes and links in frontotemporal regions that are the ones that are contributing the most to the predictions of the model. And then when we train on participants from non-Latin American countries and we apply these to participants in Latin American countries, we have the distribution of ages, which is skewed to the right. So essentially what this is showing is that the participants in Latin American countries have older ages than those in the normative sample on the non-Latin American country dataset. So this is showing that essentially there is more accelerated brain aging in the Latin American countries relative to the non-Latin American countries. This is essentially showing the same result, but using this different visualization. And what's interesting is that we also find that this accelerated brain aging is manifested more severely in Latin American countries for the female participants. So we have a higher brain age gap in the Latin American country for the female participants only. Using the EEG data, we have similar results, also good quality of the model, good accuracy. We have, again, frontotemporal regions that are the ones that are contributing most to the predictions of the model. Then we have, again, this positive brain age prediction gap in the Latin American countries when we train the model using the non-Latin American country data. And finally, we have also that the females have larger brain age gaps in the Latin American country set compared to the males. Concerning the patient groups, what we see is that there is a continuum of brain age gap values that goes from healthy controls to patients with Alzheimer's disease and frontotemporal dementia. So this is as expected. The mild cognitive impairment group have more larger brain age gap compared to the controls, but then the Alzheimer's and the frontotemporal dementia have larger brain age gaps compared to both the MCI and the healthy control groups. We see this for fMRI, we see this for EEG, and we see an interaction between the patient group and the gender. Essentially, what we see is that patients in Latin American countries, essentially only Alzheimer's disease patients and healthy controls as well, as we said before, present larger brain age gaps than those those that are male, but only in Latin American countries. So we've seen that in non-Latin American countries, the brain age gap between males and females is similar for all of the groups that we investigated, and there is a similar result for the EG data as well. Then we trained gradient boosting regression models to predict the brain age gap based on several features that are both related to the clinical status of the participants, essentially the disease status of the participants, whether they have different diagnoses of Alzheimer's disease, frontotemporal dementia, where they were considered in the mild cognitive impairment group. But we also have macrosocial and economic data. For example, we have the Gini value for each country or region, and this is an aggregate measure of the level of economic disparity. And then we have other aggregate measures, for example, air pollution quality, air pollution levels, so essentially air quality metrics. We have also the factors representing different the prevalence of different communicable and non-communicable diseases. And when what we see is that both models resulted in relatively good predictions of the brain age gap based on these factors that can be considered both clinical and environmental or contextual, or more broadly the exposome of each participant. And what we see is that not only the models performed well for Latin American countries and non-Latin American countries, but also we see that some features were more important than others. So we did 3 different feature importance analyses. We did the Shapley method when we use the mean permutation importance of the gradient boosting regression. We have also another independent method to estimate the feature importance. And what we can see is that in both groups, the most important features had to do with the disease status or the presence of neurocognitive disorder in the participants. But we also see that there were other important factors, especially from the Latin American countries, where the Gini index was important according to all the 3 different criteria. But this was not observed in the non-Latin American countries. So essentially, the level of socioeconomic disparity what predicted accelerated brain aging only in the Latin American countries. And finally, and I think this is very important, we show that uh, data quality metrics were not behind these results, because there are several different scanners that were used in this study, several different centers. Some of the scanners, of course, were a higher field, others were a lower field. Different sequences could lead to different data quality. So this showed that there were essentially no differences in the between groups depending on the data quality of EEG and fMRI data. So very rapidly, the fMRI data quality was estimated in terms of the signal-to-noise ratios, essentially the ratio between the mean and the standard deviation of short epochs in the fMRI time series. And the EEG data quality was estimated similarly based on the variance of the signal, and also the presence of different artifacts that can be identified in the EEG signal. And what we see is that there were no differences in these metrics depending based on the different regions and the different patient diagnosis for the comparisons. And we also see that the brain age gap could not be predicted by data quality that we estimated from the ECFMI data. So it's not a bias that we have to be concerned about in the model. So to wrap it up, what we showed in this paper, or what Sebastian mostly, who is the one again that did most of the work, showed in this paper is that the brain age gap can be reliably and consistently estimated from EEG and fMRI data. And he also showed that Latin American countries have participants with larger brain age gaps that compared to non-Latin American countries, and this is a regional effect. The paper also shows that female participants from Latin American countries have larger brain age gaps compared to male. This is valid from both for healthy controls and Alzheimer's disease patients. Of course, patients with Alzheimer's disease and frontotemporal dementia also have larger brain age gaps compared to both controls and MCI. And we also observe this effect of larger brain age gap comparing Latin American countries to non-Latin American countries in the group of Alzheimer's disease patients. We could predict the brain age gap based on the disease status and the Gini index, but the last one, the Gini index, only for Latin American countries. And finally, the results could not be explained by data quality or demographic biases. I did not show the, um, the analysis concerning demographic, the possibility of demographic biases in the data, so gender, age, education, and other important factors, but you can take a look at the paper and it's explained there. So thank you very much for listening to the presentation. And if you have any questions, you can send me an email or you can also contact Sebastián or Agustin.